Hello and welcome to the lesson on linear motion, where we're going to discuss the differences between distance and displacement, speed and velocity, and also look at what is acceleration. So first of all, the difference between distance and displacement. I think this is a concept that's best explained by drawing a simple thing like a map, and then looking at the difference between the distance and the displacement of something on that map. So here's the axis of a map. North, east, south, west. And we're standing at the origin. And there's some kind of object 10 meters to the east and 10 meters to the north. I'll mark it with a cross. So coordinates 10, 10. The distance between you and that object, people naturally intuit this, it's the length of the straight line from the origin to that object. But the displacement is not just the length, but it's the direction and the length of that line. So that explains what I've written here. Scalars like distance and speed fall under the category scalars, has magnitude, which is another way of saying size. You can describe the distance to something in terms of size. You can say, I'm 100 kilometers from Melbourne, or I'm 100 meters from the finish line. And it's very simple because all you're saying is the length of the straight line between you and the finish line. But you're not telling me anything about the direction. If you were to say, I'm 100 meters west of the finish line, you've just given me a vector. And you've given me the displacement of you in relation to the finish line. Or in fact, that would be the finish line in relation to you. So displacement is, we could say, this yellow arrow here under the green arrow. It has direction and magnitude. That is displacement, which is given by S. And the distance is simply the length of this green line here. So displacement and distance are related. But as I'll say it again, displacement has direction and magnitude, and distance only has magnitude. The relationship between displacement and distance is given by Pythagoras. If we look more closely, I have to delete this text here. At the triangle that these form, the yellow arrow forms a triangle with far side length 10 and horizontal length 10, and the length of D, well, we can follow the formula D squared equals 10 squared plus 10 squared. D squared equals 200. D equals root 200, which I think equals about 14.1 meters. So this object on the map is 14.1 meters distance from the origin, but its displacement is given by the coordinate 10, 10. Distance is very useful just for giving you a rough idea how far apart objects are, and displacement is a lot more useful later in physics when you want to map out exactly in a 3D space an object is. So now we've discussed distance and displacement. We can talk about speed and velocity. Now, the units for speed is meters per second. We'd use kilometers an hour in everyday language because that's what we're used to doing in our cars. Speed is given by distance over time. Fix that T. Distance over time. Now, speed doesn't tell you again anything about the direction. It's a scalar. It simply tells you how quickly something is moving through space. That's very useful for cars, cricket balls, things like that. But it's lacking in information. Whereas velocity, which units also are in meters per second, tells you both how fast the object is moving and in which direction. So if I sketch, this vertical axis can represent the sky. That would be, we'll say, height, and the horizontal is x, and there is a ball falling to earth. The speed we can represent with the length of this arrow. It's how fast that ball is moving. And let's say the speed again is 14.1 meters per second. That is the speed. But the velocity we have to describe in a different way. We could describe the velocity. Say this is coming down at dotted lines, not so good on this software. This angle here is 45 degrees. That means this ball is moving down at 10 meters per second and across at 10 meters per second. So this is the interesting thing about the velocity. We don't just talk about, the direction the ball is moving, measuring along that axis. We measure the velocity along the axes of our choosing. So saying a ball is moving at 10 meters a second down and 10 meters a second sidewards is not a paradox. It can be doing both those things at once. It simply means if you only look at the height of the ball, it is moving down that height at 10 meters a second, and then if you only look at the horizontal movement of the ball, it is moving across at 10 meters a second. But of course, in real life, when you're looking at the ball, it'll be moving on that slant because of the combination of those two components to the velocity. So since speed is a scalar, it only has magnitude. It's very simple to say the speed is just one number, 14.1 meters a second. But since velocity has direction, we need to have these components of the velocity. We can break it down. In a 3D world, we would break it up into x, y, and z components. So we could pinpoint the way a ball or a particle is moving through a 3D space. So velocity gives you a hint at how fast the ball is moving, but it gives you exactly in which direction it's moving. Let's look at why velocity is superior to speed. Say you were standing in the middle of a roundabout and you were watching a car go around the roundabout, and you're on a walkie-talkie describing that car to someone. If that car is moving at a constant speed of, say, 10 meters a second, then every time that person calls you on the walkie-talkie, you'd simply say, oh, hey, the car is moving at 10 meters a second and it's not changing. That is the speed. That is the speed you're describing. But if you were talking about velocity, you have a lot of information you could give this person. At this point in time I've pictured here, it's moving at 10 meters a second to the left. Shortly after, it'll be moving at 10 meters a second down. After that, 10 meters a second to the right. And after that, 10 meters a second up. So if you can describe both the speed, or the magnitude and the direction of that car's movement, you'll be giving them more information. Now let's look at this not so diagrammatically, but graphically. Say there was a straight line, and that straight line had an origin, and there's a particle moving around that straight line in that fashion there. It goes to 1 meter, goes back to -1 meter, and then it shoots off. Since this displacement occurs along a straight line, we don't really need two coordinates. We can just use one coordinate. So displacement units S, I will say this is in meters, and then we can have time along the horizontal axis. This ball moved to, negative here, start at the origin, moved 1 meter away, we'll say that happened by maybe the 2 second mark, and then moved back, we'll say that happened at the 6 second mark, so 2, 4, 6, and at the 6 second mark it was 1 meter behind, and then it moved off again. We can graph the displacement of that object. Up, down, and then up again. Now, this is interesting because if I asked you, what is the total distance the object has traveled by the 6 second mark? You'd say, okay, it went 1 meter in this direction and then 2 meters in that direction. That's 3 meters. But if I asked you what is the displacement at the 6-second mark, that would simply be -1 meters, as shown by this graph. Now the last interesting thing I want to show with this graph is that the gradient of this line is equal to delta S over delta T, which is the change in displacement over the change in time, and that is equal to the velocity. And in this case, since it's in one direction, also the speed, but don't worry too much about that. It's equal to the velocity. The gradient of a displacement versus time graph is the velocity, and if we graph the velocity below that, it looks like this is moving at 0.5 meter per second for 2 seconds, so d equals vt. If it moved 0.5 meter a second for 2 seconds, d equals 1. It did move 1 meter to the right. The graph would look like this. -1/2. So the displacement was moving in a positive direction. It was moving in a positive way on the axes, which is why we have positive velocity. And then we can have negative velocity as the object is decreasing its displacement. It's moving towards the negative side of this axis. Displacement and velocity can be negative, but distance and speed can't, because it's silly having a negative distance. I mean, what are you describing with a negative distance? Describing behind you, in the opposite direction to you're looking, it's nothing. But a negative displacement is simply saying, I've got a set of axes, I'm saying that maybe east and north are positive, but this object is southwest, so it has negative displacement. And if it's moving in the southwesterly direction, its velocity is also negative. So in this region of the graph here, it's moving in this direction, which is, I'll highlight the part of the graph that corresponds to there. Now the final thing, if you take the area under the velocity time graph, that area is equal to the displacement. So say I won't take that much area, say I take the area just up until there. This area down here, A, is equal to this area B, but B of course is a negative area, so A plus B is equal to A take away the magnitude of B, and that equals 0. And lo and behold, on the graph above, at this point here, the displacement is 0. So the gradient of a displacement time graph is the velocity, and the area under a velocity time graph is the displacement. Now acceleration. Acceleration applies to velocity only. If we have, say, a car driving away from us at a single speed, sorry, not at a single speed, at a constant acceleration, the velocity time graph will look like this. It started at a standstill, and then its velocity increased like that until it reaches a maximum. The acceleration is equal to the gradient of this line. So the gradient is equal to delta V on delta T, and that equals acceleration. The units of acceleration, well, it's delta V. V is in meters per second, and T is in seconds, so it's meters per second over seconds. That's meters per second squared. Acceleration describes the change in velocity over time. Now, if we had a box sliding along a frictionless surface, and the box started with a velocity of 10 meters a second, and then a second later the box had come to a standstill and V was equal to 0 meters per second. This is the positive direction there. Then the change in V is equal to the final velocity, take the initial velocity, that's -10. The change in time, we said the change in time is equal to 1. So the acceleration equals delta V on delta T. That is equal to -10 on 1, -10. So if an object starts out with positive velocity and experiences a negative acceleration, we would say in simple language that is a deceleration. So acceleration, velocity and displacement can be both positive and negative. Scalars can be only positive. In physics, we mainly deal with displacement, velocity and acceleration because it's much more descriptive. Distance and speed have very limited applications. Get used to dealing with graphs of these elements of linear motion because they reveal a lot about the behavior of a particular object.